That's the
So there's a Piazza question right now. Someone just asked what chapters are covering for the final. That's literally what I'm going to do in this review session. So if anyone wants the free Piazza participation, they can go get that right now.
You're about to get 20 comments.
Do we get a cheat sheet?
You do, yeah. So I updated that. You will get a cheat sheet for the final. I think one of the professors didn't have cheat sheets for his exams. Yeah, but I think the other two did, so we're going to have a cheat sheet.
How are you going to decide the participation rates based on Piazzas?
Essentially, like, there's like an overall contribution, like just like the amount of stuff you contributed, and then there's like good questions, good answers. Like I can see all this stuff, so I'll have like a way to do it. Essentially, the average Piazza grade I'm going to give is probably going to be like the average attendance grade in Zach's class, just to keep it fair between the two classes. So that way, like one person isn't like getting, like one person doesn't just have a lot of extra credit, while the other person doesn't.
Okay.
Okay, so yeah, let's get started. Hopefully I'm streaming. That way this will be recorded as well. So yes, this is streaming. All right, so welcome. Thanks for the water. So I think what I'm going to do today is I'm going to do essentially this is going to be like the cheat sheet review session. So I'm not going to talk about any like examples in detail, but what I'm going to do instead is give a really broad overview of like the entire course and what I believe should be emphasized when you're studying going into the final. And to end it off, I have like 30 true-false problems we can go through. So that's going to be about what today's plan is.
Are we going to have true-false?
I don't know. So the thing about the midterms is that like I knew what's going to be on the midterm. The thing about the final is I have no idea what's going to be on the final. So I literally can't tell you like how long it is. I can't tell you what sections are going to be emphasized. Like you're not going to have like the section by section breakdown like on the midterms or like the audience sends out an email. So that's not going to happen. So what you have to do is essentially be prepared for everything. But more or less, there's going to be a few things that are going to be emphasized on the finals more commonly than not. Okay. So yeah, so not a very rigorous review session. The next review session, so I'm holding one, I think on the 17th, right, from 7 to 9:30 p.m. I actually have last year's final, which isn't on the website, so we're going to walk through that final during that review session. So I guess that's going to be cool. But other than that, today, nothing too particular. So I'm like open to take like any questions right now. Does anyone like have anything about the final? Like any lingering questions? Yeah, let's go, David.
So this is the material we covered this year. Is it less than previous years? Like
It is. Yeah. So I think Jordan form, you guys did like the last day of class, right? So that's like technically fair game for the final. I think the one thing we didn't cover is like nonlinear systems. So if you see like a 2x2 like system of equations and they ask you to like classify it in terms of like stable node or like unstable spiral or something like that, I don't think that will be on the exam. Again, I don't know what's on the exam, but it's like if Davi never covered it, I really doubt it's going to be like on the final. So I think you guys have really ended up 2 sections short, and then some of the optional stuff as well. But so just like the last 2 sections of the textbook were not covered.
Are we gonna be expected to know 3x3 or effective matrices that are larger than 3x3?
You could. I mean, it could be a question that they give to you. So 3x3 matrices, I think I covered those extensively. I mean, I went through pretty much every example that you could have for a 3x3 defective. I don't, even larger, I mean, I don't want to rule it out. It could happen. I guess like for a 4x4, we can maybe talk about that the next review session, or we can talk about like generally here a little later, or like even larger. But there's like a method to deal with them, so they're not that bad. If you know the 3x3 case, you can essentially just like generalize it to higher dimensions. Any other questions? Okay, so why don't we get started then? We're actually gonna get kicked out at 4 because people actually are reserving these rooms since it's finals week. I guess a few other announcements. So there's like the daily practice problems I've been posting, which essentially goes through each section of, I guess, the textbook every day. So the idea was to break it up into more manageable like daily sections. So I know like the exam's still a week away, and a lot of you have other exams to study for. And so the goal of the daily problems then wasn't to like force you to spend like 2 hours just like doing the problems. You should be able to do them like 20 minutes or so, and they should provide like a good refresher of like the previous topics for the exam. So I would keep up with those. I think I have 3 sets of like problems completed for there. So we have like square matrices, something else, and then I just did rank, nullity, and all that stuff yesterday. So I don't know if I would post something tonight, but I'll post something tomorrow. Okay, let's jump into the stuff. So what is on the exam? So according to the syllabus, right, we have the following sections. So chapter 2 is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. Okay. 2.1 introduces matrices. 2.2 introduces matrix algebra. And 2.3 introduces systems of equations. Okay. So I think like pretty clearly that there's no reason for the professors just to like test you guys on this stuff, because it's going to be implicitly tested in everything else, right? We've been dealing with matrices the entire semester, so why would they just ask you to define a matrix or like compute some matrix algebra? You're going to have to do it anyways. Okay, systems of equations, I mean, like, there's like a few definitions here. I guess a consistent system and an inconsistent system, like you should know what those are, but really it's just definitions for systems of equations. Okay, let's see. 2.4 is row echelon form. Okay. And again, like this stuff gets implicitly tested and everything else. It's more or less just, can you know the vocab behind it? So for row echelon form, of course, there is row echelon form, and then there's like reduced row echelon form. I don't think there's really anything else there. Yeah, not really. Okay, and then rank, but we all know what rank is, so that technically gets introduced in 2.4. 2.5, this is Gaussian elimination. So a common type of problem, so it's not likely, I mean, I'm not going to say this is going to show up, but if something shows up here, what's going to happen is they're going to have a matrix, and then they're going to have like an unknown entry in the matrix, and it's going to be like, what value does this have to be for this system to have a solution? And a lot of times, like, if it's like a really like long and rectangular matrix, you can't just take a determinant, right? So you actually have to like row reduce the entire thing. I mean, that's really the only thing that's going to happen from 2.5. So a common problem, I guess, long rectangular system of equations, and I guess like find a value in the system that satisfies the system of equations that allows a solution to exist. Okay. What else? I mean, like reducing is pretty easy. Know what like free variables are and know how to deal with free variables. What else? Know how to set up the augmented matrix. And I think that's more or less it. I mean, you need to know the elementary row operations. Right, where the elementary row operations, again, we switch two rows, we add a multiple of one row to the other, or we just multiply a row by a scalar. These should be fairly, you shouldn't have forgotten these because we've been using these the entire time. Okay. 2.6 is the matrix inverse. Okay, we know what these are. I think, like, implicitly, this will just be tested in other areas. Like, we use a lot of things about determinant and, like, the matrix inverse. You can also, like, talk about, like, basis and the matrix inverse and stuff like that. So just by itself, the matrix inverse isn't going to be, like, you're not going to get a problem that gives you a 5 by 5 matrix and, like, go invert this matrix, right? Because that'll take you half the exam just to do that. So that's not going to happen. I mean, again, a really common problem would be like, you have a square matrix, there's some unknown in it, find the unknown such that this matrix is invertible, right? Like stuff like that. Nothing you haven't seen before. So again, that's more tested with the determinants though. So that's chapter 2. Again, nothing, so chapter 2, I would doubt that there's a question that just straight up asks you to do something in chapter 2. If it is, it's going to be the first question of the exam, and the first question of the exam is almost always like a softball thrown at you guys just to get you like going on the exam. So that would be something that shows up. Okay. So any questions about chapter 2? Okay. Chapter 3. These are the determinants. Okay, so chapter 3, there's really like no sections that we go through, right? It's just like a bunch of methods of determinants that you can figure out. So a few things you can know. The first one is like the geometric interpretation. Of the determinant. All right, and if you remember, it's signed volume, right? So that's what it is. It's signed volume. So in 3 dimensions, it's like, okay, if I have 3 vectors, linearly independent vectors, and find the determinant, it's the volume of that parallelepiped that it spans. Right? In 2 dimensions, it's going to be the volume of the parallelogram, or the area of the parallelogram. So it's assigned volume because we can deal with more than just 3 dimensions, and so we just call it volume. What else? So there's methods of finding determinants, right? So the first one is going to be cofactor expansion. And I would say cofactor expansion is going to be your go-to on the exam, because what's going to happen is that when you find eigenvalues, eigenvectors, right, you need a characteristic polynomial where you need to find the determinant, right, of a minus lambda I. And what usually happens is there's going to be some row that's going to have zeros everywhere else that you can just expand on, right? And that'll make your life easier. So no cofactor expansion well. I'm not going to cover it here, but again, there's a lot of videos. We've done this for a long time. The second way to do it is going to be row reduction. Okay, so remember, if you reduce your matrix to an upper triangular matrix, and then you can just take the product of the diagonals to get your determinant. What you want to also keep in mind is that you want to keep it. You want to know the effect that elementary row operations have on determinant. So a common problem where if we just straight up ask you something about the determinant is going to be one of those problems where you get like a 3x3 matrix and it just has A, B, C, D, E, F, G, H, I, right? And then we're like, find the determinant of 2A plus 3B, like 7H plus 6I, whatever, right? And then you have to like work backwards to get your determinant. So that's going to be a type of problem that you might see. So is a determinant find, yes, let's do it this way. Find the determinant of a matrix with unknown entries. Given some other determinant. Right, so we've seen this before, we've talked about it. I don't think there's really anything else about determinants. And I guess I'm just going to write it down, but know that determinant of A equals not equals 0 implies both ways that A is invertible. Right, so that's the big deal with determinants. That's pretty much the only reason why we care about determinants is because if the determinant is non-zero, your matrix is invertible, and then because the matrix is invertible, right, we have a bunch of equivalent things, right, that come from the fact that a matrix is invertible. So know that, and that's about it for chapter 3. Again, it's going to be tested implicitly, especially in the eigenvalues, eigenvectors, where you have to find the characteristic polynomial. Okay. Any questions? Okay. So, chapter 4. Okay, so chapter 4 is vector spaces and subspaces. I guess we're just going to call it vector spaces. And so this is going to be a chapter where I guess stuff gets really abstract and I guess more confusing for a lot of people. So chapter 4, chapter 4.1, right? Chapter 4.1 is just common vector spaces. but we really didn't talk about this chapter. What we really cared about was the fact that right, a real vector space gets its scalars from R, and a complex vector space gets its scalars from C. So remember, a vector space has to be defined with some notion of addition, some notion of scalar multiplication, and where the scalars come from in scalar multiplication tells us what kind of vector space we have. Okay? And I would say in this class, this semester at least, we've pretty much only dealt with real vector spaces. I can't really recall a single instance where we've asked you to find anything inside a complex vector space. So if a problem doesn't say if it's a real or a complex vector space, it's going to be a real vector space. And like 99% of the time, it's going to just be a real vector space anyways. So all our scalars in this semester, they came from the real numbers. We didn't have any complex scalars most of the time. Okay. Let's see, what else? So that's that. 4.2. Okay, so 4.2 is a definition of vector spaces. Okay, so what is the definition of a vector space? Remember, a vector space, we have a set of elements, V, a field of scalars, which is, again, usually R. Some notion of addition, so an addition operation. Which we call plus, and a scalar multiplication operation. Which we called dot, right? And so these four things, in order to satisfy the definition of vector space, they had like those 10 axioms in the book, right? If satisfies 10 axioms, then this is a vector space. Okay. And if you've been following up with the daily problems that I've been posting, you're going to realize that, you know, sometimes, right, we call it addition operation because it's not just straight up addition. I can define addition weirdly in some way, or I can define scalar multiplication weirdly. And if I do that, it can still be a vector space. It might not be a vector space, but just know that it's not just bashing vectors together in terms of addition and scalar multi. Okay, let's see. Any questions on vector spaces so far? Okay, 4.3, subspaces. All right, so remember, a subspace is a smaller vector space inside a larger vector space called V. All right, so V is our big vector space. Then our subspace is going to be a smaller vector space inside. And smaller vector space in what sense? In the sense that, okay, let's call this subspace S. Okay, so the subspace S. So it's a subspace if the dimension of S is less than the dimension of V, or less than or equal to. All right, and to check if S is a subspace, we had to do two things. The first thing is we had to check for a closure under addition. And the second thing is to check closure under multiplication, or scalar multiplication. All right, and the thing is, these two things imply, so if they're both true, then the zero vector exists. Okay? Or if both hold, then the zero vector exists. Okay, so one way to check that if something's not a subspace is you can just check for the zero vector not existing, right? And so if the zero vector doesn't exist, then it's not a subspace. If the zero vector does exist, it doesn't mean it's a subspace. So this arrow only goes this one way. It doesn't go both ways. So you need to check then if the zero vector holds, then you need to check closure and scalar multiplication by itself. Okay. And a very important subspace then that gets covered in this section actually is the null space. All right, where the null space of A is the set of all x such that ax is equal to 0. Okay, so the null space is a subspace, and we deal with the null space a lot more in the other sections following this section. All right, 4.4 is span. And so I think we're at the point where midterm 1 happened. I think we're right around the span and linear independence stuff. So a lot of this stuff will get brushed aside because it was crammed for midterm 1. So it might be a good idea to study a little bit what's going on with span and linear independence. But the definition of span, right, is the following. And let me do it like this. All right, so span by itself, there's a few ways it can be used, right? It can be used as a noun, or let's see, is it a noun? Yeah, okay, so one way it can be used as a noun, and the idea is that the span of a set of vectors v1, v2, all the way to vk. So you have k of these vectors, right? And so the span of this set is the set of all linear combinations c1 v1 plus c2 v2 plus ck vk. All right, so if you have a set of vectors, the span of the set of vectors are all of its linear combinations. All right, so that's when it's used as a noun. It's used as a verb when we say a set of vectors spans, okay, a vector space All right, so a set of vectors spans a vector space if every vector in the vector space. So actually, let's see. Let me call this vector space something, V. So a set of vectors spans a vector space V if every vector in V in V, little v and big V, can be written as a linear combination of vectors in the set. So I guess I should give the set a name. So set S of vectors spans a vector space if every little v in big V can be written as a linear combination of the little guys in S. And so if you span a vector space, you're not necessarily a basis, right? Because you could have extra vectors scattered inside, right? So for example, let's just talk about the xy plane. I can give you 1, 0, I can give you 0, 1, right? And then I can give you 3, 3, all right? Well, these 3 vectors, they span R2, right? Because you have 1, 0, and you have 0, 1. So obviously, you're going to hit every vector inside R2. And then I also gave you 3, 3, which is just an extra vector, but that extra vector doesn't unspan the entire thing, right? You still have your axes, right? So, so essentially, span, like, if your set of vectors spans, then you're really close to being a vector, to being a basis for a vector space at that point. But you could have extra vectors. Okay. So what are some types of problems that show up? So there are 4 of them. So given a set of vectors called S, find its span. All right, this one's the easiest. You just slap some constants on in front, and then you're done. Right? You just literally, you're given a set of vectors, so you just slap these constants, C1, C2, on front of them. And that's the, just add the constants in a linear combination of vectors in S. I mean, you literally just write, you just write this down here, and then you're done. Okay, the second way to do these, second problem is, given a set of vectors S, determine if it spans Rn, okay, or some vector space, usually Rn. I guess let's just say some vector space, big V. Okay, so if you're given a set of vectors and you want to determine if it spans a vector space, big V, what you have to do is you have to set up an augmented system. Right? On the left-hand side, you'll put the S vectors. And then on the right-hand side, you'll put like a general vector in V. All right, so this is going to be like a general so it's a general V in V on the right-hand side. So for example, right, if I'm asked to find if V equals R3, you'll put your vectors, right? You'll put S in here as column vectors, and then on the right-hand side, I'll put X, Y, Z, since like X, Y, Z is the general 3-dimensional vector in R3. Right? And then what you want to do is you want to make sure that this augmented system is consistent, or in other words, you can actually find a solution to the system of equations. Okay, so S equals X, Y, Z, and then, let's see, S, and then if consistent, then spans. Yeah?
Does it matter if you get like infinite solutions, or do you just get?
No, so, doesn't matter if you get infinite solutions. Let me think. So, so you should only end up with one solution. That's what you should end up with. I guess what happens if you have too many vectors, then you'll have infinite solutions. The idea is this last row, you can't have like 0 here, and then you have like something like there. That's the only thing that can't happen. Or like you can't have a row of zeros and then have something that is conditionally non-zero. Right? So if like you have a row of zeros, but on the right-hand side you have like z minus x, right? Then it doesn't span because you need z minus x equals 0 for that system to work. Yeah.
So then those are all just like variables like in the vector, like in the vector space.
Where? Which vector space?
On the right-hand side of the augmented matrix.
Yeah. So in this case, right, x, y, z is your vector in R3. Right, and then it's just the general R3 vector.
Sorry, what are the first 2 words in blue?
In blue, I'll add a constant. Any other questions? All right, so that's number 2. Number 3 is where's the sheet? Okay, and I guess I should say if row of 0 on the bottom, there's 2 things. One, if the right-hand side is 0, then you're good. If the right-hand side is not equal to 0, but a function of unknowns, then that function of unknowns is what these vectors actually span. All right? So the function of unknowns on the right-hand side is going to be the subspace that the vectors span. Yeah.
Like, once you write in red, all of them.
Oh, it's like a general v in v, right? So it's just your general vector in the vector space. So for example, in R3, I just put x, y, z on the right-hand side. Okay, so that's 2. Number 3 is given a vector space, or given a set of vectors S, determine if V lies in the span of S. All right, it's the same thing as above, except on the right-hand side, you put whatever vector V they gave you. Okay, so it's the same as above, except make the augmented system V, whatever V they gave you. Okay, so instead of seeing if you span a general vector space, now all we care about is if you span some particular vector in that vector space. And so then we just do the same thing. You set up the same augmented matrix. You put your vectors in the set on the left-hand side, and then you just put whatever vector they give you on the right-hand side. And then you see if it's consistent or not. Okay, and then number 4, given a vector space, find a spanning set. That's really just find the basis. So I guess given a vector space, find a spanning set. Really, you just find a basis for that vector space, right? Because the basis has to span the vector space. And so, and we know, do you remember how to find bases? I guess I'm getting to that, so it's fine. Okay. Any questions? Okay, 4.5 is linear independence. So the definition is the following. Vectors v1 through vn are linearly independent if the solution to c1 v1 plus c2 v2 plus ck vk equals 0, all right, is c1 equals c2 equals ck equals 0. All right. Another way to put this is the following. So we can put our v's as the column vectors. Right? So you put your v's on column vectors, and then you're going to have these constants c1 through ck multiplying so this would be c2, right? So if you write it out in a matrix form, you put your v's in the columns of a matrix, and then you line up your constants c1 through ck as a column vector. Then this has to be the 0 vector, right? And, well, this just equals 0, actually. And the idea is, okay, actually, that's the 0 vector, this is the 0 vector. And the idea is if C1 and C2 all the way through CK are all 0, that's the only solution to this system of equations, all right? And if that's the case, then you're linearly independent. So what does that also mean? Well, if we call this matrix A, right, and we call this vector a vector of C's, right, and I forgot only right here, which is really important. It's the only solution.
Otherwise, it would be the null space, right? If it had like more than one.
Yeah, yeah. Otherwise, I would have been given the definition of null space. So if we rewrite this, right? So we've taken this step to this step to this step down here, and so we've rewritten everything. You have A times C is equal to 0. So linearly independent if the nullity of A is 0, right? Because the only solution we can have to the system is the 0 vector, which means that the null space of this A matrix that we created, it can only be the 0 vector inside that matrix. And so, or inside that null space. Right? And so therefore, if nullity of that matrix that we made is 0, then all of these vectors, v1 through v, I should call that k. Oh, my notation's not very good. But if v1 through vk are linearly independent, then this is going to be true. Does that make sense? So do you see the link between where we went from like the seemingly like one sentence of equations to like talking about nullity in null space? So this is kind of where that happens. Okay. Okay. And if any other C1 through CK exists, or if any other C1 through CK satisfies this system, then it's dependent. And another thing is if A is square, then invertible implies that the columns, these V1s are independent. Right, because if you can invert the matrix, that means the null space has to be 0, which means the columns are independent. All right. Let's see, that's the wrong color. 4.6 is bases. Actually, you know what? To save some time, what recitation is this? This is, I think, though, there's like one recitation where I did like the cheat sheet for the review because it was on like Thursday, right? And I went from 4.6 to 4.7, 4.8, 4.9, 6.1 through 6.5. Okay. So this is recitation 9, I think. So for 4.6 through 6.5, we want to look at recitation 9. It's the exact same thing I'm doing here, except I went through those sections. And so that's probably going to be better use of our time if we don't cover that here. Okay. Any questions? Any questions about anything up to chapter 7? Yeah.
I missed the part when you talked about nullity.
Okay. Yeah. Yeah.
Yeah, they just came in.
Yeah, I just said that null space is
Okay.
this thing. I didn't really talk about it in detail.
Okay.
Nullity itself, I think.
Is this really a big portion, or it's going to be?
Well, with null space, like column space, row space,
Yeah.
null space, they're all very like intertwined. And I think if you look at the daily problems from yesterday, I think I had a pretty decent write-up
Okay.
of the relationship between column space, row space, and null space. If you do those problems, that should also give you like a really good
Okay.
idea of how they're like interlocked with each other.
So the final is going to be pretty evenly distributed.
No, it's not. It's not. It's not.
It's going to be heavily.
It's going to be heavily towards the end. That's what always happens. So I guess for row space and column space, let me just say the following. Call space,
No, bitch.
null space. Take a look at the daily problems from 12:11. There's a pretty good write-up there, I think. And then 6.1 through 6.5, those are like the matrix transformation stuff. I think we spent a lot of time on those linear transformations before the midterm, right? Of like the 3 types of problems that you'll see for linear transformations. So I would say, I think I cover it pretty in detail in this video too, so it should be good.
That's 9, not 4.
9, yeah. Whichever one says like review, like it's a recitation review essentially, yeah.
Thank you.
Okay, so let's talk about 7.1. So 7.1 is eigenvalues, eigenvectors. And okay, so what are some results then of eigenvalues, eigenvectors? It's really important to just be able to go from the definition. So remember, we have AV is equal to lambda V. Okay? Or we also have A minus lambda I times V is equal to 0. And recall that these two definitions are the same thing. One of them is just everything moved over on one side, and the other one is AV equals lambda V, whatever the definition that is. In this case, right, V is an eigenvector, and lambda is an eigenvalue. Okay, to find these, we need to solve determinant a minus lambda I is equal to 0 for the roots. Lambda. And this determinant a minus lambda I thing, this is the characteristic polynomial. All right, and one thing I want to point out for the characteristic polynomial is that very rarely are we trying to make your life hell with finding the characteristic polynomial. So on this past midterm, if you realize that the characteristic polynomial was shit, it's because you made a mistake. It really shouldn't be bad, unless for some reason we really want to make you guys find some like complex eigenvalues. In that case, I think we would just give you the complex eigenvalues. So be suspicious if your determinant or this determinant of a minus lambda I looks really bad, because I would say 90% of the time you're the one at fault. And if you can't get this to work out correctly, I think I just gave you 3 points on the midterm on that problem. Like there's nothing more I can really do. So don't get stuck here with the characteristic polynomial. Okay. 7.2. And this is like some that. Let's see what the syllabus says. So it says eigenvalue, eigenvector general results. Okay, so the important thing to know is that, okay, there are a few things here. So multiplicity is the number of times like lambda shows up, or a particular lambda shows up in the characteristic polynomial, right? If lambda has multiplicity 1, it must have exactly one associated eigenvector. Okay, so if your lambda shows up once, right, you should be able to find at least one, you should, not at least one, well, you should be able to find one linearly independent eigenvector, right? If you can't, it's the wrong lambda, right? If you find more than one, you're doing something wrong. Okay, so if it shows up once, that's as much as you can do. If lambda has multiplicity, let's say k, all right, then there's two cases. If you have less than k, well, let's say you have k eigenvectors, linearly independent eigenvectors for a minus lambda I, right? Is that the way to do it? If you have k linearly independent vectors for lambda, in other words, the nullity of a minus lambda I is equal to k, then it's diagonalizable and non-defective. So they're the same words. Diagonalizable is what non-defective means. And if lambda, if you have less than k linearly independent eigenvectors? I.e., nullity of a minus lambda I is less than k, then it's defective, and then you have to deal with the whole Jordan form shenanigans and whatnot. Okay, so there's that. Some other general results, we might as well talk about them right now. The sum of the lambdas is equal to the trace of A, right? And the product of the lambdas is equal to, what you call it, the determinant of A. All right, and another thing that we talked about is if nullity A is not is like some, let's say, value n that's greater than 0, then lambda equals 0 is an eigenvalue with multiplicity at least n. Right? Because remember here we're looking at the nullity of a minus lambda I, and so if we're just looking at the nullity of A, that just means lambda is 0, right? And that means that, okay, if the nullity of A is not trivial, then we have eigenvectors for lambda equals 0. Right, so in this case here, if nullity is A, right, remember, up here we're looking at A minus lambda I, so if we're just looking at the nullity of A, we're implicitly implying that lambda is 0. That's what that means. Okay, 7.3, can move on now. Diagonalization. So essentially, if A is diagonalizable, in other words, for every lambda, the nullity of A minus lambda I is equal to the multiplicity of lambda. Okay, so for every eigenvalue this has to hold, then then what? Then A is equal to S ds inverse, right? Where S is some basis of eigenvectors, D is lambda 1, lambda 2, whatever, all on the diagonal, and then S inverse is this first guy inverted. And just remember that whatever lambda is, right, so if this is like lambda 1, if this guy here is lambda 1, that's in the first column. Then the first column of S has to be the eigenvector, right, that's corresponding to lambda 1. So you can't just, so for example, if I find an eigenvector for lambda equals 3, then, and I put 3 here, then that eigenvector has to go here, right? What else? Do you guys talk about similar matrices in class? McGrath-in? Okay. Alright, I don't, do you guys
Yeah, he said it like once.
say it once? Okay, it's not a big deal. I think, yeah, I don't think being similar is that big of a deal. So that's fine. I guess you can go read the definition of similar. I think, don't quote me on this because I'm not even sure off the top of my head. I think as if you can diagonalize them, like if they have the same D matrix, they're similar. Don't quote me on that. It's in the book somewhere. It's a short definition. It's actually not that bad. Okay, 7.4 is the matrix exponential. Okay, so I'm not sure if this section is actually going to be like explicitly tested. Did Davi do this on the last day? Did he do this did he do this during the what you call it, the systems section of the class? Okay, it doesn't seem like it. I thought about it briefly. What do I want to say?
We just went over defective matrices on the last day.
Okay, that's fair. So matrix exponential then, I'll just talk about it real quickly. It's e to the at. All right, and so if a is diagonalizable, then e to the at is equal to s e to the dt s inverse, right? So essentially what happens is S is that basis of eigenvectors, and then you got your e to the dt, which is just e to the lambda 1t, e to the lambda 2t, etc. on the diagonal, all the way up to like e to the lambda nt, and then you have S inverse as the last matrix. I talked about this in recitation like real briefly, but if it's diagonalizable, this is how you do it. Okay, that's good because then you guys don't have to find exponentials for defective matrices. If you never talked about the matrix exponential in general. Okay, so that's 7.4. I think 7.6 is Jordan canonical form. And I'm just going to refer you to recitation 14 because that's all I did in that recitation. So. All right, chapter 8. ODEs. Let's see how we group these. So 8.1 through 8.2, I guess Davi did like 1.6, right? Which was first order ODEs. Essentially, just know how to use the integration factor. Oh yeah, this was on your last exam. Okay. What else? 8.1, 8.2. These are homogeneous ODEs. Right, it says linear differential equations and constant coefficient homogeneous linear differential equations. So what? Essentially, I mean, these are really easy, right? The homogeneous differential equations, like there's like literally a formula just to follow every single time as a process. The only thing that could happen is like be careful of like an initial value problem, but other than that, I don't really see anything that much with these guys. Okay, 8.3 is undetermined coefficients / annihilators. So what goes on with these is the following. So you have that table of guesses, like, right, it's in your textbook. I refer to you guys to that table like a trillion times. Should probably be on a cheat sheet somewhere on the final, just in case. Know what happens when you have like, when you need like multiple annihilators, right? What you do with like your annihilators then. So like multiple annihilator situation. And what else? So this is a not very used method. Although I think it showed up on your midterm, but it's not like the best way to go about things. So it's like only use if the right hand side is simple enough. I guess that's like the best way to put it. Right, so if you have like e to the something x, like that's fine. But if you have some mess, then you really can't like guess it away. (8.4) is complex value trial. So I would say, I think this did not show up on your midterm, right? Okay, so I think it's a very good chance that this will show up on the final. I would say just know when you use this. I'd say a good chance this shows up on the final. I'm just gonna put it that way. I mean, I think it'll show up, especially since Davi like covered it in class apparently for a few days. So they'll put it on the final. Or I mean I don't know what it looks like, but that's what it's going to be. 8.5 is oscillations or like spring mass systems. Let's see. So for spring mass systems, this one I've only seen it on like 2 finals in the past, so I don't think there's actually a good chance it shows up. It also showed up on your midterm in place of complex value trial, so I don't think they'll put another one on the final. Again, I just really don't like talking about these things because it's just vocab. So this, again, it's a bunch of vocab. I think on your midterm, it wasn't really a spring mass problem. You could actually just do it with physics, right? No, it was more like, do you know how to do algebra? So, yeah, so as you can see, like spring mass problems, they're not like real like spring mass problems. They're just like some kind of differential equation that you have to solve. Okay, 8.7 is variation of parameters. This is an optional topic. It's not going to be directly tested. Although I think it's better than annihilators, especially for second order ODE. So the way I did it was for second order ODEs that looked like y double prime plus ay prime plus by is equal to some right hand side. But other than that, like it doesn't matter. So a and b can be any constant coefficients. Our 8.8 Cauchy-Euler. So y'all kind of got baited on this one. This kind of did show up on the final, on the last midterm when he like asked you to solve for the homogeneous for like that x squared y double prime differential equation. That's actually this section. You don't actually need to like know how to use this section, but just like in general, like I guess now you've seen it on the midterm, like fool me once, okay, shame on me, like not shame on you, but fool me twice, whatever. Whatever that J. Cole line is. So you put it's the x to the x squared y double prime plus ax y prime plus by is equal to f of x. Actually not f of x. Let's just make it 0. And in your solutions, then what you want to do is you want to take you want to guess y is equal to x to the r as a solution to the homogeneous. And then, so what happens is you get like x squared, and then y double prime of this guy becomes r minus 1, x to the r minus 2, plus a x times r, x to the r minus 1, plus by is equal to 0. And then this becomes r minus 1, x to the r, plus ax to the r, plus, and this should be bx to the r is equal to 0. And then from here, you can just get rid of the x to the r's. So just we don't need these guys. And then you have this like polynomial to factor. And then you get your r, and you plug it into x to the r. Right? So you just put it into the power up there, and then from there you can use like reduction of order to solve your problem. Yeah.
What's like the pattern for 8.7?
8.7 is variation of parameters. Okay, so this is Cauchy-Euler. Uh, 8.9 then is reduction of order. This is, I think this is going to show up on the exam. This almost always shows up on the exam, so there's a very good chance, high probability, this shows up. Yeah, it's a very good chance this thing shows up. So, I mean, you guys just did it for an exam, might as well just like do more reduction of order problems. There are a few of them on like the previous finals and whatnot. So. Okay, so now let's go to systems. So 9.1 and 9.2 are like the intro sections. They're not very important besides like a few niche problems that can show up that could ruin your day potentially. The first one is converting a second order diffie-q into a first order system. And the second one is, whatchamacallit, if you get like a non-homogeneous, like an inhomogeneous system, I don't even know, is it non-homogeneous or inhomogeneous? Non-homogeneous. So for like the non-homogeneous 2x2, you had to like, on Piazza say you had like guess, which was a way to do it. Another way you could do it was to like, you had to like set up a system of like D's, and they had like cancel out the D's. There's like an example in the textbook where they do it. I doubt it. I actually haven't seen this. Okay, there's one problem that's been a non-homogeneous system that's been on a final, and the way you did that problem was through a trick. So I don't think this is going to show up, but the first one might. Okay, 9.3. I guess 9.1, 9.2, 9.3, just lump these all together. 9.4 is then your general solutions, x prime is equal to ax when a is non-defective. Right, so this is essentially just find the eigenvalues, eigenvectors. And then you throw them into that like general solution type. So that's not bad. And then 9.5, I think there's a high chance that something from 9.5 is going to show up with a 3x3 defective matrix. I don't think they're going to go higher than that, but I'm pretty sure they'll put like some 3x3 defective matrix on the exam. So this is x prime is equal to ax when a is defective. All right, and then so again, now you just have to work with the Jordan form. And in that Jordan form video, we like solved all of these systems of equations, right? So I talked about like, okay, so once you have your Jordan canonical form, you have your basis of generalized eigenvectors. Now, how do we solve the general system? We talked about that in that video as well. So that's in the recitation 14 video that I told you guys to watch earlier. Okay, so I think this is it. I think here is where it stops. I don't think there's no 9.8 or there's no 9.8, 9.9, 9.10. Or I think, wait, hold on. 9.8 is the exponential. I don't think you guys got to that, right? So yeah, so that I don't think there's going to be 9.8, 9.9, 9.10. I don't think these are going to be on the exam. So yeah, so we stop here, and that's going to be.
So not 9.6.
Yeah, 9.6 isn't even on the syllabus, so it's not going to be like, on the exam. Yeah. Okay, so that's the whole thing. Okay, so let's see. If I had to take a bet, like if I had to place bets on what was going to show up, there's one. So I have 12 questions. So there's one question. Here's another question. So 9.5, 8.9, 8.4. So that's 3. They usually have quite a few diffie-Qs, so they'll like throw you like an easier diffie-Q in here. So they'll have another diffie-Qs. So I guess, what should I say? So there's gonna be 1 or 2 from here. There's gonna be 1 or 2 problems here. I'm gonna guess you're gonna see around 3 diffie-Qs. And then I'm gonna guess you're gonna see 2 to 3 problems from here with eigenvalues, eigenvectors. They might lump those in with, so again, for the eigenvalues, eigenvectors problem, they might ask you to like find like some matrix power, right? So that was like a application of the diagonalization, like a to the 1,000, like what's that matrix? So that might be something, so I'd say like 2 problems here. So what am I at? 1. So I said like 3 diffie-Qs, 2 of those, 1 of these. So that's like 5. So let's say they do like 12 problems. All right, that's 5 or 6. And then this vector space stuff, they'll give you like 2 of them. They'll give you like one linear transformation probably. Maybe more, at least 1. They're going to give you like 2 vector space problems. Let's say there's a 1 true false section. And then, I don't know, they'll give you like 1 problem from chapter 2 and chapter 3. So what's that? So that's 5 problems right there. These 2 problems here get you to 7. This gets you to 10. And then this stuff here gets you to 12. So that's going to be your exam probably. Yeah, I'll scroll through this again. So,
Thank you.
so where was this? Yeah, so you'll notice that the majority of the weight's going to be towards the latter half of the class, right? So starting with chapter 7, that's going to be like the most of the weight. So if you're like really crammed for time, like I would study like the eigenvalues and eigenvector stuff like really well. because essentially eigenvalues and eigenvectors gets you through chapter 7 and chapter 9, right? So that like knocks out two sections at once. And then ODEs, you're essentially just guessing anyways, right? With a lot of algebra, so ODEs are ODEs.
Problems coming from the later.
Yeah, so you're gonna have 2 in chapter 7, and then in chapter 8 you'll have 3 of them. You'll probably have one of them be like one of these easy ones. You're gonna have one of them come from complex value trial, I think, and then you're gonna have a reduction of order problem. And then in chapter 9 you'll have 1 or 2, and one of them is gonna be a defective 3x3 matrix. Okay, any questions? Okay, let's take a 5-minute break. We'll come back at 3:30, and then we'll run through these 30 true-false questions I have. So,
Ivan,
yeah.
so for those of us who had McGrath, our last midterm was pretty much like a fake shit show, I'll say. She did not really go over it. I personally don't think it really went over any material that I wanted to learn.
What did he put on there?
It was basically half physics.
Oh, so you just put a lot of spring stuff?
No, it wasn't springs. It was like pendulum shit.
Yeah. Like,
No. We learned springs. So it's half. Also, part of my class are physics majors, so they didn't really know what everyone else learned. But for the effective portion, he didn't. I don't think he even got to that class. Or if he did, it was like the last 10 minutes of it. Do you have like any extra practice from the last?
yeah, I mean, my last recitation only went through those problems. Like, that's the only thing I did. Yeah.
Is there any way that like any of us can see your guys' midterms?
I can show you my.
Okay, that would be.
Yeah, midterms 3, so we're handing them back. So I have them. Yeah, I have office hours after this. And then, let's see, midterm 3. Yeah, I mean, midterm 3. Our midterm 3 was like really standard.
Okay.
Like there was like no surprises on it, besides like the last problem, which wasn't that much of a surprise either. So, yeah. So like everything you see like on a final is like pretty much what our midterm 3 looked like. Okay, so he said he would do for number 2, like he did for midterm 1, right? And then he said he would for midterm 2, and then he didn't. So they're on like the lecture canvas. So there are like 2 canvas sections. There's like the recitation canvas section. And the, yeah, no, I don't think he put them. I think he put them on canvas. They're in the email. Like midterm 1's in the email.
So obviously you don't want to go through it and do like the A minus lambda
Right.
Yeah, so that thing, right? So to row reduce.
You can't row reduce.
You can't.
No.
Cannot. Yeah.
So if you have some big matrix, like let's say you have something that looks like, for some reason you have an exam, it looks something like 1, 9, 9. Oh, okay, so I remember the one on that exam. It's like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1,
But it's like if you just write it, you will get 0. So I did. She said it's a good.
It was like this guy, right? Like on the exam, it might have been 3.
It was 3. Yeah.
It might have been 3. But okay, let's say you have like 1s, right? So here, what we want to do is that these, so this nullity is 4.
And then I had integral
Right, because this dies, like these all dies, right?
and then I had x
So that's like the only
and then x cubed ln of x. And I literally, I had all
right,
these
you can
separate
cancel it and see what the nullity is, but then you kind of just have to do it. Okay, now they're all back. Right, so you know the nullity is 4. And then from this guy right here, we say that if nullity is some n that's greater than 0, right, then lambda equals 0 is an eigenvalue equals c greater than 0. Okay, so in that case, our nullity is 4. Right, so lambda equals 0 is an eigenvalue with at least 4. Right, so right. So lambda equals 0, both greater than or equal to 4. All right. So now you have to see, okay, what can it be? It can be 4, it can be 5. Right? Because it can't be 6 because I only have 5 columns. 5. Right? So if nullity was 5. Right? What would happen? If nullity were 5, well, the trace has to equal the sum, right? But the thing is, the sum is 5. Right? So then I can find my other eigenvalue because. Well, because it has to be at least 4. Well, it can't be 5 because then my trace is 0 and that's wrong. So multiplicity is 5. And so multiplicity is 4. It's equal to 4. And the trace is 5, so the last eigenvalue is 4.
So let's say you were row reducing.
Yeah.
If you kept some of the diagonals of the trace, the original matrix.
No, because then the product has to be equal. Yeah. So you can't row reduce in
No, that's what I'm saying. I'm taking it as a
Okay.
Oh.
Yeah, we're like, thanks.
All right, let's go through. So the true false problems I had. One of them. So I managed to get my hands on some midterms from the semester I took it, and it was actually the other professor's midterms. And if you're not familiar, I took this class with Bob Powers. So if you're sophomores, you've probably heard of some amazing stories with him last semester. I can attest to every single one of those stories. So, but in any case, I have the other TA's midterms, the other professor's midterms. So there's a bunch of true-false problems, and then I have some true-false problems as well. So let's go over mine first, because mine are a little harder. So this is like true-false based on like eigenvalue, eigenvector stuff. And here's the first one. So stop me if I went through this problem, because I don't think I did. I think I like kind of shied away from a lot of eigenvalue true-false, because if I remember correctly, we like kind of just smushed eigenvalues and eigenvectors like the week before the exam of midterm 2. So I don't think we ever talked about these in detail. But anyhow, if A is a square matrix such that A squared is equal to A, then 0 and 1 are the only possible eigenvalues of A. So true or false? If A is a square matrix such that A squared is equal to A, then 0 and 1 are the only eigenvalues that I have. Let's do a show of hands. How many people say true? Okay. True, true. All right, few. All right, how many say false? One. Any false? False? Come on, we're just all guessing here, right? All right. Yeah. All right, that's fair. So, okay, let's work this out. So this one actually, this one's true. Okay, and so for the, I guess it was like 60-40 guess. So for 60% that said this was true. All right, good job. But this is more like of a proof type of true-false problem. The justification is actually really interesting. So it's the following. So let V be an eigenvector for lambda. Okay? Then from the definition, we know that AV is equal to lambda V. Right? So this is by the definition of what an eigenvector is. Okay? And then, now what? Okay, well, we know that A squared is equal to A, but we haven't really used that yet. So now we know that A squared V, all right, so what is A squared V? A squared V is equal to A times AV, right? Just pulling the A out. But what is AV? Yeah, it's lambda V. So now this is A lambda V. So lambda is just a scalar, right? It's an eigenvalue. So I can just pull that out in front. All right, so now it's lambda times AV, but AV is just lambda V. All right. Which is lambda squared V. Okay. But what do we know? Well, we haven't used this fact that A squared is equal to A yet. So if we use that fact, then we see that A squared V is equal to AV, right? Because A squared is equal to A. So A squared has to be equal to A squared V has to be equal to AV, right? You're multiplying the same vector. Well, what is A squared V? A squared V is lambda squared V, right? And what is AV? Well, AV is lambda V by definition. Okay? And so now what? Well, now you see that, well, lambda squared has to equal lambda. And how many of those do we have? Well, this is really the system lambda squared minus lambda is equal to 0, right? And you see that the solution, then, it has to be a lambda equals 0 and 1. So those are the only two solutions to the system. So that's pretty cool, right? If you have a square matrix where A squared is equal to A, you know your eigenvalues already. They're 0 or 1. Those are the only possible values they can be. Okay. Any questions? Okay. Number 2. If you have a non-defective square matrix, non-defective square matrices with only one eigenvalue have the form lambda times I. So is this one true or false? All right, so if I only have one eigenvalue, then if I have one eigenvalue and it's non-defective, then it's just an identity matrix, but then with like a scalar multiplying it. So it's essentially like 5s on the diagonal, or like -7s on the diagonal, right? It has to be of that form. So does that make sense? Is that true or false?
Oh.
Do you have an idea?
It wouldn't be false because then you'd have if you only have if it's not effective you can only have ones. So you have to have like a 1 by 1 identity.
Well, so let's just think of the identity matrix itself, right? So the identity matrix itself is just 1s on the diagonal, right? So what's the eigenvalue? Just 1, right? With like, and the multiplicity is however many times it shows up on the diagonal, right? Because if you subtract, because A minus 1I, right, and A is the identity matrix, you're literally just subtracting 1s off the diagonal. So then you get the 0 matrix, right? So then that would be fine, right? Because you get the 0 matrix after you subtract 1 off the diagonal, right? So that would be fine. So this is actually true, and maybe the proof will be a little enlightening. So non-defective, this is the first fact that we want to use. So non-defective implies that A is equal to SDS inverse, right? We can diagonalize the matrix. So now the second fact we want to use is that there's only one eigenvalue. So what does that mean? Well, to only have one eigenvalue, that means D, right? D is just lambda, 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 right? It's just the same lambda repeated on the diagonal. Okay, so given these two facts, what can we do? What can we do about it? Well, okay, so A, right, is really equal to S times this D, S inverse. Okay. So I can factor out that lambda out of that middle matrix, right? Because it's just lambda times that identity matrix. It's the same lambda. So then this is S times lambda I S inverse. Right? This middle matrix is just equal to lambda I. Right? It's lambda times whatever identity matrix that, whatever size that matrix is. And then what? You can pull lambda out in front. So now you got lambda S I S inverse. And from here, you just simplify. This is lambda S inverse, right? Because S times I gets rid of that identity matrix. And then this is just lambda I, since S inverse is equal to I. So yeah, A is equal to lambda I. So that's also true. Okay, last one. Okay, the last one might be a little more intuitive. So if A is square, if A is a square matrix and it's diagonalizable, then so is A squared. True or false on this one? If I can diagonalize A, can I diagonalize A squared? True? Yeah. All right. So yeah, this one's true, and this one kind of seems like it has to be true, right? If A, you square it, like, what do you really change about the matrix? And this is one of those like applications of the squaring things that we like to do. So, right, A is diagonalizable, right? Means that A is equal to SDS inverse. So now we want to investigate what A squared is. Well, A squared is equal to A times A, which is really SDS inverse, SDS inverse. And then you get a lot of canceling. So you get S, D, and then S times S inverse. This is just the identity matrix. So we can just drop that. So now we got S, D, D, S inverse. And now this is S, D squared, S inverse. Okay? Is D squared a diagonal matrix? It is, right? Because D is a diagonal matrix. So a diagonal matrix times a diagonal matrix ends up being a diagonal matrix, right? So yeah, so D squared is some diagonal matrix. Who knows what it is? It's just the original one squared. But you still have the same eigenvectors, right? This is the same S as in A. Right? So these guys are the same thing. So, I mean, so you still have the same basis of eigenvectors, so it's diagonalizable. Okay? You just have different eigenvalues. So same basis of eigenvectors. So diagonalizable, it's true. All right, any questions on any of these three? Okay, let's go over some diffie-Q ones. All right, so this is number 4, I think. I said there would be 30. We haven't gotten to like the easier ones yet. Okay, so PD of y is equal to f of x. All right, so are we familiar with this notation? All right, so this is just the differential equation. You have some like polynomial of your derivative operators acting on y is equal to f of x, which is the right-hand side. Okay, so PD of y is equal to f of x, and then f of x is non-zero. Okay, the general solutions y of x form a vector space. True or false? Okay, so that's I mean, vector space is a very it's a much broader definition than just linear independence, right? So I would say, yeah, so you're right in that they're all linearly independent, but any other ideas? Yeah.
Is it because like the right hand side can't be 0, so it's like failed like one of the closure under addition? Or
Yeah, you're exactly right. So it fails closure under addition because any general solution, if you add it to another one, you're going to get double the right-hand side, right? Another easy way to see this is that the 0 vector doesn't exist, right? Because the right-hand side is non-zero. So if you plug in 0 into y for your general solution, it doesn't exist, right? So it's not going to be a subspace of a bigger function. And if it doesn't include the 0 vector, it just can't be a vector space itself. So this one's false. 0 is not a vector, i.e. it's not a solution to the inhomogeneous diffie-Q. Right? Since f of x not equal to 0 implies this is inhomogeneous, we can't have 0, so this one is not a vector space. Okay, 5. All right, we got the same setup. PD of y is equal to f of x. All right, now I'm not saying anything about the right-hand side. Say PD is degree 3. In other words, i.e., you have C1 y triple prime plus C2 y double prime plus C3 y prime plus C4 y is equal to some f of x. If y double prime at some point is equal to y2, y prime at some point is equal to y1, and y at some point x naught is equal to y0, then the solution is unique. In other words, these guys are just some initial value conditions. Okay? So if I give you a third order differential equation and I give you these initial value conditions, then I have a unique solution for my differential equation. So is this true or false? Yeah.
True.
Why?
Because you had a constant for each one of the values.
Okay. So yeah, more or less that's right? Because for each one of these for each one of these like initial value conditions, you're going to be able to isolate like one. So I guess the easier way to say it is here you have one equation with 4 unknowns, right? Here's your second equation, here's your third equation, here's your fourth equation. So now you have 4 equations with 4 unknowns, and you should be able to solve this system. So yeah, so you have the correct number. This is true. You have the right number of. You have enough initial value conditions to determine all the unknown coefficients. Okay? So for a third order differential equation, you need 3 initial value conditions. For a second order, you need 2 initial value conditions. And then I guess for like a fifth order, you need like 5 initial value conditions, right? So you need all the way up to y to the 4th prime in that case. Yeah.
So, like, even if you have the same number of equations as you do, like, unknowns, could you not get, like, no solution? Or is that considered?
So for initial value problem, you're going to be forced, it forces you into a solution.
Okay.
And the reason is because all your solutions are linearly independent anyways, so you're not going to run into, like, that problem where, like, you have the same, like, constants running around. Okay. So yeah, so for a system of equations, so usually where you're going to see this is like a second order differential equation. We give you y and we give you y prime, right? And then that's enough, and then we let you go solve your system. So that's that one. And then, let's see, 3 p d of y is equal to f of x. All right. Okay, so say that y1 is equal to 3 e to the negative 2t plus e to the t is a solution. And say that y2 equals 3 e to the negative 2t minus e to the 5t is a solution. Then e to the t plus e to the 5t. Ooh, my handwriting looks really bad here. I mean, it always looks bad. But e to the t plus e to the 5t is a solution to the homogeneous PD of y is equal to 0. Okay, so true or false? Right, so I give you 2 solutions and I say, oh, this one is going to be a solution to the homogeneous.
Do you have to just check if it's like a linear combination of like the 2?
So not quite just a linear combination. Because a linear combination. No, that's true. Because no, it's not. Because remember, from the first problem, right? We said that the general solutions do not form a vector space, right? So you can't just do linear combinations of your general solutions because they're not necessarily closed under addition. Okay, so yeah.
Is it false because y1 has, or they share the term 3 e to the negative 2t, so that's the yh, like the solution of the matrices?
Not necessarily. Right, so what we could have done is that we could have had like some equation, right, where it's like c1 e to the negative 2t plus c2 e to the negative 5t plus c3 e to the t, and then we just set like one of the coefficients to be 0, and the other coefficient could be 0, right? And then we could have ended up with something like this. Any views? Okay, so for sake of time, I'll just give this one away. It's true. And why is it true? The idea is the following. The difference between any two particular solutions is a homogeneous solution. Right? So if you think about it, right, how do we get from one particular solution to another? You take a particular solution and you add some homogeneous solution to it, right, and then you get another particular solution. Right? So in terms of like the null space, right, we're like sitting on a point and then we shift it by something in the null space, right, and then we're on another solution point. So the idea then is if I have 2 points that I know are solutions, if I take the difference between them, right, then that has to be the shift by like the null space, or in this case, right, a homogeneous solution. So in this case, right, if you take y1 minus y2, you get e to the t plus e to the 5t, which is a homogeneous solution.
Oh, is that because like if you plug in the particular solution, you would get f of x? So if you subtract the
Right, exactly. That's one way to think about it, right? If you plug in a particular solution, you get f of x. So if you subtract two particular solutions, you're subtracting the f of x on the right-hand side. Okay. Any other questions? All right, I'm going to wrap it up because I know that someone wants this room at 4. So I guess I'll just like sprinkle these other 27 true false I have into the daily practice problems. So, all right. So thanks for coming. Again, I'm going to be here Monday at 7 p.m. I think. I think the idea then is to go over last year's final, which is unreleased. So no one's going to have seen it before, which is cool. And then yeah, I think with that, that's about it. So again, in order to study for the exam, remember look at the daily problems I'm posting. And I think if you want to, like maybe just run through all like the previous, recitation videos and stuff like that, just to like refresh yourself with